Hello, in today's video we're going to be discussing section 7.3 on logarithmic functions. So logarithmic functions are functions that are inverses of exponential functions. What they will do is they will take your exponential function and solve for the exponent. So for example, say I've got 2 to the power of x is equal to 8. Now hopefully we already know that 2 to the power of 3 is 8, which means that x must be 3. So I can go ahead and just say here that x is equal to 3. But maybe I have something like 2 to the power of x is equal to 17. And that's not a number that we know right off the top of our heads because 17 is not a power of 2. So what we can do is rewrite this using log functions and solve for the value of x. So in our equation in example 731, I have y is equal to 10 to the power of x, and they're asking us to estimate the value of x when y equals 500. So what I'm trying to do now is say that y is 500. What is the value of x that gives us that value of 500 for y? So I can use the graph because 500 is not a power of 10. So I'll go to about here, 500 for y. I'm going over to my graph. I see that I have an x value that's a little bit more than 2.5, so I'm going to go with 2 3/4. So x is going to be approximately 11/4, or 2 3/4. Now again, this is just an approximation because we used a graph, we did not use logs to solve for the exact value of x. So a logarithm is going to take your exponential function and isolate the exponent. So here I have b to the power of y is equal to x. Well, the log function is going to isolate that y, so y is going to be equal to the log with a base of b of x. Now this log base b of x cannot be separated. It is one component, so we can't divide by x because it's not multiplication. This log is a function, and x is the input of that function. Just like when we have f of x, this is not multiplication. This is saying that we are inputting x to our function, so we read it as the function of x. So we read this very similarly, log of x. And the b tells you what you are raising to the power of y. So b and x cannot be separated from your log function. I'm going to go ahead and practice writing these logarithmic equations in exponential form. So 6 is the base of my exponent. I go across the equal sign, and 1/2 is my exponent. And then I make a full circle back, and this will equal to that square root of 6. This would be exponential form of my logarithmic equation. Here I've got log with a base of 3. So 3 is the base. It's the base of the log, and it's the base of the exponent. So I start at the base. Log base 3 of 9 equals 2. So 2 is my exponent. Exponent is always isolated when you're talking with logs. Is or equals 9. So taking this out of log form and back into exponential form, I have 3 squared equals 9, which we know is true. Going backwards, I can go into logarithmic form. So I know that my exponent's going to be isolated. Then my base of my log is the base of the exponent 2. And we are going to have log of 8 because 8 is what we are equaling. So here I've got 2 to the power of 3 is equal to 8. We make a full circle. So I'm going to go ahead and do this one more time. I can also write this using that same kind of swirl pattern if I write it with the log on the left. So log base is the base of my exponent, so 5, of 25 is, and then my exponent is always isolated, 2. All right, go ahead and take a moment to pause the video and try rewriting these next 4 equations in logarithmic form. In B, I should have log base 10 of 1 over 10,000 is negative 4. Here I've got log base 2 of 1/2 is equal to negative 1. Log base 13 of 169 is equal to 2. And log base 16 of 256 is 2. And going backwards, I've already shown you a couple of these, so go ahead and take a moment to pause the video and try setting up these 6 on your own. First is 5 to the second, which is 25. Second is going to be 3 to the fourth is 81. Third, 11 to the negative second power is 1 over 121. All I'm doing is going from the base to the other side back to my log expression. So the base is 225, exponent is 1/2 equals 15. Base is 15, exponent 2 equals 225. Base is 14, exponent is negative 2 is 1 over 196. And those would be your 6 answers for these 6 questions. To evaluate logarithms, what we are going to do, I prefer to do at least, is to set them up as an equation. So I'm going to go ahead and say that this is equal to maybe a. And we are asked to determine each of these without using a calculator. So I'm going to go ahead and set this up by saying this is 4 to the power of something is equal to 64. So I am looking for the exponent on 4 that gives me an answer of 64. Well, what I can do is write 64 as a base of 4. So 4 to the power of 3 is going to be 64, which means that a has to be 3. So what I have found is that if a equals 3, I need to actually answer the question. There was no a in my original question. So I'm going to go back here and say that this log simplifies to 3. Log base 4 of 64 is 3. In C, they are asking us for the exponent that we put on 121 to get 11. That is what this entire expression is saying. So I'll go ahead and let B be the exponent. So 121 to some exponent equals 11. Well, I do know that 11, if I square it, I will get 121. So what I'm going to do is write 11 squared. This is 121, so it matches that left-hand side, but it doesn't match my 11. So I also need to undo that squaring. So I'm going to write this with a 1/2, because power of 2 and a power of 1/2 are inverses of one another. So what I've really got here is 121 to the power of b is 121 to the power of 1/2. So this is 11. I just squared it and then square rooted it to have my base in terms of 121. So that tells me that b must be 1/2. So I go ahead and say that the value of this expression, the exponent that I must put on 121 to get 11, is 1/2. All right, pause the video and try those next couple. Here I've got 3 to the power of y is equal to 1. I know that anything to the power of 0 is going to be 1. Anything non-zero to the power of 0 is 1. So that tells me that 3 to the y is actually equivalent to 1, which is 3 to the power of 0. Now that my bases match, I know that my exponents must match, so y is equal to 0. Here I am trying to find the value of the exponent that I put on 2 to get 1 over 32, so I'll go ahead and let this be maybe d. 2 to the power of d is equal to 1 over 32. I know that 32 is 2 to the 5th power. And since 2 is in the denominator, if I write that as 2 to the negative 5th, it will no longer be in the denominator of my fraction. So 1 over 32 is equivalent to 2 to the negative 5th power, which means that d is equal to negative 5. So I can go back and say that this expression is equivalent to negative 5. All right, I've got a couple more for you to try. Go ahead and try these out after pausing the video. Number 1, we should have 4. Number 2, we should have a negative 3. Number 3, we should have 2. And number 4, we should have a negative 2. Common logs. Common logs are simply your standard logs with a base of 10. However, since this is our standard log, we don't write the base. So for example, just like in these cases, there are invisible ones. There's an invisible 1 as a coefficient on my x. There's an invisible 1 as exponents, and there's an invisible 1 in the denominator. So all of these have those invisible ones that we don't write. We just assume that they are there. Just like these, your common log is assumed to have a base of 10. So if I say give you something like log of 1,000, I did not write a base. So just like I didn't write any of these blue ones, we assume that this base here is 10. We don't need to write it because it's just your standard or common form of your log. So in these cases, we're going to evaluate them without using a calculator. So here I've got a 10, and I'm trying to figure out what power I need to raise this to in order to get 1,000. So I start with my invisible base, 10. I raise it to some power to get 1,000. And that power that I'm going to need is 3. So simplifying this expression, I find that I get 3. All right, go ahead and pause it and try those next few on your own. In C, we're going to have a 0. In B, we're going to have a 1. And in D, we're going to have a 10 to the negative 1 to 3/4 power. So that would give us a value of negative 4 for our exponent. In example 736, we're talking about energy released from an earthquake. In this earthquake, it was 500 times greater than the amount of energy released from another. So this equation represents our situation where x is the difference in magnitudes on the Richter scale. We're going to estimate x by first rewriting the equation in logarithmic form and then evaluating it using a calculator. So 10 to the power of x is equal to 500 in logarithmic form. This means log with a base of 10 of 500 is equal to x. Now we do have buttons on our calculators that say log. Some of them you put the 500 in first, some of them you type log first. So go ahead and play around with your calculator until you get the answer of x being approximately 2.698. Once you have practiced enough, you'll figure out exactly how your calculator intakes your log functions, so you can use this to verify. The last case that we have is a natural log function, and we abbreviate this as NL. So instead of log, which has a standard base of 10, the natural log is a very specific case of log. It is a log function with base e. So log of base e we actually write as ln. So in these cases, I have e as my base, and we are to evaluate this expression. So I'm going to go ahead and start off the same way I did before. I've got e. I'm raising that to a power of m, and I get e to the 1/3. Which means that my exponents must be equivalent. So m is 1/3. All right, go ahead and pause the video and try those next 3 on your own, and in just a moment I'll have you check your answers. C should be 0, e to some power equals 1, so that power is 0. Here e to some power is the square root of e, or e to the 1/2, so that power is 1/2. In this case, I would go ahead and divide by 25, and then we can write an equation and solve. Solving, I find that m is 10. That's the end. Thanks for watching.